Now light, you've probably heard that light has a wave-particle duality. It means light can behave as a wave, light can behave as a particle. That means if light is behaving as a wave, it can experience all the wave properties. Reflection, refraction, it can interfere, we can have interference from light, and so forth. Those are wave natures of the light. The particle nature of light is when light actually interacts with another piece of matter. So for example, if light hits the board, it hits an actual dot on the board. If you, in your book, if you get a chance to look at it, I don't have a book with me, they show photographs of different exposure times with light, and you can actually see little dots of color. The lowest exposure is just little dots of light that have been kind of hard to see. But low exposure, you get really just fine little dots where the light hit the film. The film reacts when light hits it. Longer and longer exposure times, you get a nice picture. But when it comes down to just the particle nature, that photon, we call it, sorry I didn't mention that, we call the particle of light a photon. It doesn't have mass, it's not a massive entity, but it interacts individually with the light itself, the film itself. So when we talk about the particle nature of light, we talk about a photon. So that's a particle. Now, it doesn't have mass, but it does carry energy. The amount of energy any particular photon has is directly related to the frequency of that particular light. It's a simple equation. The energy of a photon is equal to h. H is a constant. It's called Planck's constant. And, sorry. Planck's constant is very, very small, 6.63 times 10 to the negative 34. The units on Planck's constant are joules times seconds. So the energy, for example, let's say we had a red photon whose wavelength was 650 nanometers. Let's find its energy. So the energy of a red photon. How do we go from wavelength to frequency? Right. So wavelength will be the speed of light over the frequency, which means frequency is the speed of light over the wavelength. So speed of light we know is 3 times 10 to the 8th meters per second. Wavelength 650 nanometers, so 650 times 10 to the negative 9 meters. So the frequency of this particular red photon, 4.62 times 10 to the 14th. The meters cancel, 1 over seconds is the same thing as hertz. To find the energy, we simply need to multiply this frequency by Planck's constant. Units, when we multiply joules times seconds over times hertz, which is 1 over seconds, the seconds cancel, so that gives us joules. So one single photon, very, very tiny amount of energy. Very, very hard to isolate one photon as well. So if you have multiple photons, you just need to multiply by how many photons you have, and you would know how much total energy there is. As a reminder, We can relate energy to power. Power, remember, is energy over time. So for example, if you know the power of a laser, and you know how long you're shining it on something, you can find out how much energy was emitted on that particular object. Questions so far? This chapter is a little disjunctive. By the way, we can write this equation in terms of wavelength. Since we know frequency is the speed of light over wavelength, we can put that in for F and write the equation in terms of wavelengths if you want. It's equivalent to what we did to solve the question, solve the problem here. That's what it is in variable form.